Right, so today, Shivara and I will lead this lesson jointly. And we've decided that we want to talk to you about geometry in particular. Right, so this is going to be a geometry focused session. And when one talks about geometry, what are some of the aspects that you had learned in school? So now this is what I was referring to, and I need you to be at the keyboard to quickly respond to us about some of the concepts that you had learned. So yes, you would have done quite a bit of trig. We'd covered that last week in the session. And then apart from learning about graphing functions, etc., when I talk about paper 2 content, you would have learned about ratio and proportion, isn't that so? So that's one of the aspects we aim to cover very briefly in today's discussion. And the second component, what's the second bit that you would have covered? Let's take a look. No responses yet, but what would you have covered for paper 2 content? Nothing yet. Shivara, what do you think we're going to be covering today?
Well, I think that geometry kind of reminds me of shapes. So one that kind of comes to mind, I guess, would be the circle.
Oh, yes. Okay. So we're doing circle geometry?
Yeah. Yep. Sounds
okay.
like a plan.
I'll write that. Okay. I'll write that down. But all of this is actually falling into what? The circle geometry. Right. So I see Malali has says circle geometry and theorems. Yes, we've got analytical geometry. Wonderful. That's another aspect of it with straight lines, distance, and all of that. But today in particular, the crux of what Shivara and I will talk about, well, it will include circle geometry, right? But what we're going to end up talking about is all of this is going to fall into the Euclidean geometry theme that you would have focused on, since I think that was introduced to you from grade 11 onwards. I stand to be corrected. Right, so we will focus a bit on that. Right, so let's recap on a very crucial result that is important when we talk about ratio and proportion. Right, so in particular, there are two important theorems that you would have learned in school and gotten exposure to with regards to ratio and proportion. So it always begins with a triangle, right? And so we start off with our triangle ABC. And then what we asked to do, or what happens in the premise of this result. So I'm going to highlight a few things for us to take note of. Right, so we have triangle ABC. And we're told that DE is a segment that is drawn parallel to one of the sides of the triangle. So here is triangle ABC. This is one form in which we could draw it, or I could have drawn it like this as well, right? So again, these are the same starting points, right? And then we have this line DE that is a segment that must be drawn parallel to the one side. So here, DE is drawn internal to the triangle if I look at it in diagram 1. And if I look at it in diagram 2, it is drawn external to the triangle, externally to ABC. Right, so these are two options that one can consider by simply looking at the premise that says you start off with a triangle and that you have a line segment drawn parallel to the one side. So when we have these line segments drawn parallel to the one side, and hence that the arrowheads indicating that it is parallel, DE is parallel to BC, it turns out that we can show that DE in fact does something very special. It divides the other two sides of the triangle. In this case, what are the other two sides? The other two sides here would be AB and AC. So it says that those two sides end up being divided in proportion to one another. But here in diagram 2, the other two sides that one considers is the entire length, meaning the extension of the triangle, because we've now extended it, and hence I've used the word extension. So the extension, which is no longer us considering AB, but it's now EB, and the other bit, which extends from D to C, right? So that is what we're working with. So how does one algebraically state that? Because now I've got a diagram, but of course this must be explained in a certain way. Well, from diagram 1, right? If I look at diagram 1, this can be explained in the following way. We say that the two sides are divided in proportion, where we write it in the following way. This tells me that AD over DB is equal to AE over EC. That's one way of thinking of it. Or, right? Or I can say that, let's see, AB. No, let me not. I can say that AD over AB is equal to AE over AC. So what are the difference between the two equalities that are written down? Well, the difference here is the following, that the first ratio on the left is talking about the half length here, right? So AD, a half length over the other line segment, right? So we're looking at, so maybe I shouldn't be using the word half length, but it's looking at the piecewise portions of the line segment AB, right? So it's looking at the two pieces that were created. And likewise, I compare that and I observe that it's equal to the corresponding ratio that is created between the two pieces from AC, right? So that's one way of looking at it. Then the other equality is telling you that, well, the one piece over the full piece on this side, on the left, is equivalent. It is the same thing as the small piece over the larger piece, right? So that's what it said. And therefore, I've got AD over AB is equal to AE over AC. Is there anything else that I could have included, Shavara? Is there another ratio that I could have written down? Because here I've got a small length over a bigger length, comparing on each side, right? So can't I do maybe a different type now?
Yeah, you could do the small length over, oh, sorry.
I can do this one, right?
Yeah.
That one over the full length.
Full length,
and
yeah.
corresponding, yeah. So
kind of like the reverse.
Exactly. So we could do that. Yeah. So let me just make that one, resize it, and then I'm going to put that in. So I hope everybody's following. Have you all caught on to what I've written down? There are 3 equivalent ratios that one could talk about if DE is drawn parallel to one side, right? So here I could write down BD over AB equals to EC over AC. Yeah, okay. So that's what we've got. And obviously, correspondingly, for the second diagram, I could do the same thing. So here, in general, I would just say, I can conclude that AE over AB is equal to AD over AC. And there are more that I could write down, because this was pertaining to the pieces of the full line segment on that side. And then again, I took the pieces of the full line segment. So maybe I could do a piece over the full line segment versus the other piece over the full line segment. Is everybody following? Is anybody lost on what I'm explaining about the conclusion in here? Please let us know in the chat box so we know how to modify any explanations. Right, so that's what it says. I'm repeating. You start off with a triangle and you draw a line parallel to one side, then it divides the other two sides in proportion. That's one direction, right? So it's an if-then statement. So we have a premise and we have a conclusion. So what follows after the word then is what I conclude. It's the conclusion. And it turns out that the converse of this result is also true, right? And what is the converse? Well, I've just labeled it theorem 2, but it's now the opposite of what was said. Thanks, Katleho. I see you say that you are following. Thank you for that. And this says that if we have a line that divides the two sides of the triangle in proportion, meaning if the DE does indeed allow these ratios to equal, if I have that equality taking place, then it must be that the line that we had drawn must be parallel to the third side. okay? So this is the opposite, right? The reverse direction of what was going on. Because if you think about it, right, whatever's in the blue bracket here, right, whatever's in the blue bracket, this is a statement, right? I'm going to call it P, right? And whatever's following after the word then, that's in the red brackets. I'm going to call the red bracket Q. So essentially what theorem 1 tells me is that blue bracket implies a red bracket, right? So if you assume P, you can conclude Q. And the converse tells you that you can do the opposite, meaning if you assume Q, you can conclude P. And then you have a double direction arrow. So when you take theorem 1 and you add it to theorem 2, you get a by implication, meaning something that moves in both directions. And what it tells you is that red bracket is equivalent to blue bracket, or blue bracket is equivalent to red bracket. That's what's happening in here. Okay, I see that someone does say that they're having a problem with audio, but Shavara has confirmed that audio is working. So Usisi Pokazi, I think it might be an issue on your side. Please try and adjust your sound settings and hopefully you can hear us. If you cannot, we will have the recording shared on YouTube, so don't stress. Okay, now I'm going to continue because I wanted to go through an example, right? So I've now explained theorem 1 and theorem 2. Okay, but essentially in theorem 2, you're given that the sides are divided in proportion by the line segment DE. And what you can conclude is that if the sides are in proportion, then it must be that DE is parallel to BC. So that's the converse. Okay, now let's look at the following example that I prepared. So we have a triangle. Well, we have multiple triangles in here. Okay, as you can see. But in particular, in this diagram, we are told that CE is 4.5 units long. We are told that F is the midpoint on OD, right? And here is OD. So F is the midpoint of the line segment OD. That's what we're told. Okay, and we're told that BO, the length, right? The length of the line segment BO is 1/4 the length of the line segment BC. We're then asked to find OE, BO, and AO. Okay, so of course we are going to be as what could I say? As logical as possible when we do this. We're going to try and see if we can apply the previous theorem, theorem 1 and 2, to get out our answer. So I want to find OE. That's what I need to solve for. I need to know what this is. Where is OE? Well, here is OE. That's OE. OE is a line segment on BC. That's what I can observe. Okay. Any ideas on how one can proceed? What do we know? Remember, F is the midpoint of OD. So if F is the midpoint of OD, what do I know? This one is just a property about parallel lines and midpoints. All right, so we observe that EF is parallel to CD, isn't that so? Because that's demonstrated in the diagram. And in particular, right, so it's a parallel line, so the distances are preserved. That's what it tells you. Okay. Meaning that the distance between any point here and any point here, right, between EF and CD remains constant. That means that the distance, this implies that FD equals, sorry, that's wrong. Let me not say that. I only know about proportion. Okay, so basically what it tells me that the two sides are in proportion. Okay, using theorem using theorem 1, that when you have a line that is drawn parallel to the other, right? Okay, I can see there's Sam Muller has responded in the chat box about something. Sam, maybe you can explain what you were trying to say, right? So in any case, let me just repeat. Theorem 1 is what we're applying, and it tells you when you have a line that's parallel to drawn parallel to one side, then it divides the other two sides in proportion, okay? So here I know that OE over EC equals to OF over FD. But I also know that F is the midpoint of OD. That's what I know. Do I actually need any of this information? I know this is 4.5 units. Right. OF equals to FD. Wonderful. So maybe I don't even need this. Right. So I know that OF equals FD since F is a midpoint. Okay, good. And then I apply theorem 1, right? By theorem 1, the sides are in proportion, right? The sides are in proportion, which implies that therefore I must have that OE equals to CE. But I know what CE is, right? So OE equals to 4.5 units. And that's how you would go about explaining this. All right, let's quickly talk about BO. Now I need to solve for BO. Right, let's take a look at it and you can tell me if you have any ideas on how we can proceed. Okay, I'll also label this as 4.5 units because that's what we now know. BO, right, I need BO. What shall we do?
We can use the ratio.
Right, let's use the ratio. Okay, so I know that BO is equal to 1/4 BC. All right, do I have the length of BC?
Not yet.
Not yet. Okay. So BO is 1/4 BC, which means that OC is 3/4 BC, right? 3/4 BC. And I know what OC equals to, right? Because OC is 4.5 plus 4.5. Are we all following that? Right? So this is 9 equals to 3/4 BC. And that tells me that I can now solve for BC. What do you get for BC when you solve for it? So BC equals to 9 times 4/3, which equals to 12. So I forgot the BC, right? I forgot the C. Right, so I've got the length of BC, and now I can take that and I can sub it in, right? So therefore, I see that BO equals to 1/4 times 12, which equals to 3. Great. Okay. So I hope everybody's followed that there. Shavara, I think I'm going to leave this bit as an exercise for the students because I think we've already seen a quick application of this result. Let's move on to the Euclidean bit. I'll stop sharing.
Okay. All right, is that visible?
Perfect. Yes.
Okay.
Okay, so we're doing Euclidean geometry. And as you can see from the slides, Shivara has now segmented this or given us a description on 4 different types of results that one would consider. So I'm not sure, Shivara, would you like to tell us more about it?
Sure. So obviously we're going to have to use a lot of theorems to get to the final answer. I like to illustrate it like if you're throwing darts at like a board, and in order to hit the bullseye, that means you're able to complete the proof. So what you have in your toolbox, or what you have, with you as a weapon, is your arrow. So you've got to basically try to fire them properly so that you can get to the final answer. So I like to consider them as them being divided into these 4 different sections. Obviously, I think the one that you would be attracted to the most is the theorem of Pythagoras. It actually comes out quite a bit. So that would be the first one. Then we've got angle at the center of a circle. There are, I think, 2 or 3 theorems that relate to it. Then we have cyclic quadrilaterals. So you've got 4 points on a circle. They would make a cyclic quadrilateral. Of course, if you just take 4 points of anything and you draw lines to connect them, that would be a quad. And then if those points lie on the circle, that means that it's a cyclic quad in essence. And then, of course, we've got tangent to a circle, which is, of course, you have your famous tan chord theorem and so on and so forth. Unfortunately, we don't have enough time to go through all the proofs, but I think we're just going to briefly state them, quickly, and then move on to an example. So, yeah. First up, we have theorem of Pythagoras. Again, you should know this quite well. So these are the proofs that are there. So we can move straight to angle at the center of the circle. So the first theorem that we have there would be that the angle a chord subtends at the center of a circle is double the angle it subtends at the circumference. So we have to break that down, obviously. We've got the angle that a chord subtends at the center of a circle. So we've got that angle AOB. All right, so we've got that. And that is going to be double the angle that it subtends at the circumference. So subtending means that you would draw chord AB, right? So you would draw a line between A and B. That would make that, can you kind of put your 2 fingers on A and B, and you kind of move up all the way to produce C at the top. That would be double that angle. So again, you take your 2 fingers, you join them at D, that's the angle at the center of the circle. Then you take your 2 fingers back to A, and then you move them all the way up to C, and that would be double that angle. So if you want to look at it in terms of that, you've got those placements on the diagram. So that would be the first theorem. Again, can't go through the proofs, but they are mentioned on the slides. I guess because we have a recording, you could pause them and then look through them in your own time afterwards. All right. Then we have the angle a chord subtends at the center of a circle is double the angle it subtends at the circumference. So this one does not have a converse. Okay, so we just have this, and there's different configurations. Again, you can put your 2 fingers kind of like on the circle, make the one at the middle, and then the angle that it subtends at the top. And you can see how it could be different, right? Especially the last diagram. I think that one looks kind of not that obvious, but it's kind of like if you're looking at it upside down, compared to the other ones. So those are the 3 different, I think, configurations that you can get. Remember, they won't be hiding in plain sight. You'll have a lot of other things happening in the diagram. But that would be basically that theorem. And then if we move to the next one, we've got the angle subtended at the circle by a diameter is a right angle. So if you look at the diagram there, we've got AB, which is the diameter. And then if you put your finger on A and you put your finger on B, and then of course subtending means that you basically follow the lines that come out of A and B to see the angle that it produces at the top of the circle, and then that is going to be a right angle. And we've got that label there. And then, of course, we have the converse. If the angle that is subtended by a chord is a right angle, then that chord is going to be labeled a diameter. So we've got a backwards and forwards thing happening there. So if angle C there is going to be a right angle, then we know that AB is a diameter. That would be the reverse of that. Okay, then we have cyclic quadrilateral. So on the right, you can see just a few different types of configurations. Of course, we've got a square. I don't think I've ever seen a square. It's never that simple. I haven't seen a square in one of those examples. I think I've seen mainly the bottom two, they always look kind of weird. But really, it's just 4 points on a circle. That would be a cyclic quadrilateral. Or you can say that another way they would say it is like, prove these vertices are concyclic. So that would be another way to ask that question. And they have 3 main properties or theorems that are associated. So the first is that the opposite angles of a cyclic quadrilateral are supplementary, or they add up to 180 degrees. So again, we can't go through the proof of that, but if we just see it over here, you can see that they would equal to 180 degrees in the diagram below there. You've got X at that angle D there, as well as B. B would be 180 degrees minus X, right? Because they're going to be supplementary or opposite angles. And it would be the same with A and C. Yeah. So that's, yes, that's theorem 5. Then we have that the exterior angle of a cyclic quad equals the interior opposite angle. So if you look at the quad, we've got A, B, C, D being the quad, and the exterior angle of that would then be C, right? We've got C1 there rather, right? And then that is going to be equal to the interior opposite angle. So that would be equal to A, angle A at the top there. So if we say that angle C1 is X, then of course, because there's a straight line there, you'd have 180 degrees minus X being that. And that would mean that A, which is the interior opposite angle, will also have that same value. And it also has a converse, right? So it says, and if an exterior angle of a quad is equal to the interior opposite angle, then the quad must be cyclic. So we've got a back and forth there. Okay, that would be load shedding, but if you can then have theorem 7, it says that the angles in the same segment of a circle will be subtended by the same chord are equal. So what that particularly means is that if you have this kind of segment here, so you would have AB being the chord, right? So if you put your finger again on A and B and you kind of get the subtending angle, that would be angle O. At the center there, that will be 2X. Again, you move your fingers to the circle and you produce D, and then you produce C. They would have the same value. And a converse of that would also apply. So that's cyclic quads. We then have tangent to a circle. Of course, this is something that we talk about where we have a tangent being a straight line, then it's going to touch the circle at only one point. If it makes any other kind of point, if it touches at any other point, then that's not a tangent, okay? Can somebody tell me what that is? While you think on that, I'll look at the chat. You can see that conversely, if you have a point on a circle, then on a circle, a line that is drawn perpendicular to the radius to this point, that is going to be a tangent. Okay, so the diagram, I think, summarizes that properly. If you have 2 tangents from the same external point, so if you have this 2 tangents from P here, you can see these are tangents to the circle. It's only touching the circle once, that is at A and at B. If it's coming from the same point P, if you produce them back to P, then these are going to be, these 2 tangents AP and PB are going to be equal in length. And then we have our famous tan chord theorem. The angle between a chord and a tangent at the point of contact equals any angle the chord subtends in the alternate segment of the circle. I basically think that they call it angles in the alternate segment. So yes, yep. Angle in, so if you take angle A there, right? I've labeled it as X. Here we go. Yeah. I've labeled this as angle X. Okay, so we've got here, we've got chord AB here, right? And we've got the angle between a tangent and a chord. So if we've got our tangent AD and our chord AB. So this is the angle between them. Then basically what that says that it equals to the angle that the chord subtends. So here's AB and the chord first subtends angle E. Can you see? You put your finger on A, put your finger on B, and subtend it to the circle. You would see that it gets X. We can label this as X. And it will label this also as X because this chord AB also subtends this angle C here. So those are some theorems that we can remember. And yeah, that's theorem 9 basically with its converse. So as you can tell, there are a lot of theorems, but we can't go into the proofs in detail. Of course, you can slow it down when you watch the replay perhaps and look through the proofs. But now it's time for an exciting example. I'll take you through this now. So example 1, we're going to go through this obviously slower than we did the proof. So hopefully you guys follow along. I'm going to try and keep the chat box up on the top to see your responses. But yeah, here we go. So it says in the diagram, you have points P, Q, R, and T. I've labeled them in green dots, okay? And they lie on the circumference of a circle. Then it says MW and TW, they're in blue, are tangents to the circle at point P and T respectively. PT, which is this over here, is produced to meet RU over here at U, right? So you've got them both meeting here at U. And then it also gives us some other information that I put on that is already on the diagram, that angle MPR, which is this angle here, is 75 degrees. Then angle PQT, which is over here, is 29 degrees. And then angle QTR is 34 degrees. And then we've labeled some of these angles as A, B, C, and D. So I guess it's not really a spoiler to say that we want to find out now what is A, what is B, what is C, and what is D. Okay, so if we go through this maybe a little slower, what do we know from the first green line? If P, Q, R, and T lie on the circumference of a circle, what do those points make? Can anyone tell me in the chat box? If we've got 4 points on the circle, what do we geometrically have? A cyclic quad. Thank you, Katleho. Exactly. So we know that that's a cyclic quad, and we can imagine that that the theorems that apply to that will, of course, so we can already start looking. Does it have an exterior angle? Do we know that the opposite angles are going to be supplementary? We already know all this information just by one line. And I think you can get really happy because you can see PQRT is here, and we've got this exterior angle D here. So we know that D is going to be the exterior angle, and that's what we have to work on. We'll come to that. Then we know that MW and TW are tangents to the circle, right? So we've got them, they're touching once kind of here. So we know we can bring in our tan chord theorem. We can bring in a whole host of other theorems, actually. And finally, we've also got some chords, right? Like, for example, QR is a chord, RT is a chord, QP is a chord, PT is a chord. We've got all of that happening. So let's take it kind of one step at a time. We're going to first work out A, then B, then C, then D. I hope everyone is, oh, okay, I can see people are already solving it. Love that. Keep that energy going. I'll just go on a little bit slower. So yeah, let's move to work out angle A. Okay, so firstly, what we notice with angle A here is that it is an angle between a tangent and a chord. Remember, we said that MW, the diagram looks slightly differently highlighted now. Remember, we said MW is going to be the tangent, and we've got PT being a chord, right? PT is just a regular chord because it's just a line between 2 points on the circle, right? So we've got PT being there, and then you've got to look at the exterior angle, or rather this angle kind of here, the angle between them, right, which is going to be A. So that's the angle we want to figure out. So we can use the theorem that says that the angle between the tangent and the chord, or the tan chord theorem, is equal to the angle in the alternate segment. And that would be this angle here, which is, as we've labeled before, 29 degrees. That's already given in the question, okay? So can you see you've got your tangent, you've got your chord, you've got the angle between them, which is A, and then you look at the chord and you figure out what angle it subtends. That basically means you put your finger on P and T and you go and touch the circle, as in like you follow this up all the way over there and on this side over here, and you will see it reaches 29 degrees. So we can safely assume that A is 29 degrees, right? And the reason would be angle between the tangent MW and the chord PT is equal to the angle in the alternate segment, which is angle Q, I guess the one that's angle PQR. Angle PQT rather. Yeah, there we go. All right, so that's the first one. Now we've got that kind of labeled for us. We've got that angle A is 29 degrees. So I've kind of put that on the diagram there. So now if we want to calculate the value of B, well, we've got that this whole angle here is going to be 75 degrees. All right, this whole angle here is 75 degrees. That's given in the question. And then we have that this is equal to 29 degrees. We just worked that out, which means it's quite simple to work out what B is, right? That's just going to be an angle on a straight line. MW is a tangent, so it's a straight line. And so if we add 75 degrees and 29 degrees, I think that gives us, if I'm doing the math right, 104 degrees. And then we subtract that from 180 degrees, angles on a straight line, and that will give us 76 degrees. So now we've got that A is 29 degrees, B is 76 degrees. All right, are we all good so far? Good. Yes, I see people have already put the answers in the chat. That's great. Let's keep going. All right, next one. So we've got angle C. Now with angle C, there's a lot going in this diagram, but we basically have to do a few things to kind of figure it out. So if I can just maybe go back a slide, you see we have to work out what C is, which is over here, which means it's a part of the 75-degree angle, right? So we don't really know what that is, and we have to work out kind of what it is. So if we look at it, we can see, okay, it is an angle between a tangent and a chord. Can we do something with that? Perhaps. But what we know already is that this is 75 degrees, right? So if we work out this piece here, which is kind of in between, then we can just subtract that from 75 degrees and get what C is. And that is going to be our plan of action, basically. So to find out what this angle is over here, we can use angles in the same segment. I take you here to Q and R. Can you see that this is a chord, right? It's just a simple line here on the circle. And if you see the angle that it subtends, you will see that it subtends this angle here, which is 34 degrees, right? It's over here, 34 degrees. And then you will see it also subtends another angle. It's this angle over here, which is what we want, right? We want angle RPQ. Again, it doesn't have a a specific vertex name, but we'll just call it angle RPQ. So we figured out what this value is. What is it? It's 34 degrees. Okay. And since we know it's 34 degrees, we know that this entire angle then here, this RPM angle, this entire angle is 75 degrees. We can just subtract it from there. And of course, we'll get 41 degrees. Okay. Everybody following that? So there could be other ways, of course, to work it out. Perhaps you could, you could kind of see, another way. You can let me know in the chat box. I think, yeah, I'm pretty sure there's another way to work it out. So I can see a few others. All right, so let's move on to angle D. Now, again, before we move on there, we already know that PQRT is a cyclic chord, right? So we know that this is going to be called an exterior angle. So really, I think, it's almost like we're working backwards. We know that this exterior angle has to equal this interior angle. Is this interior angle only 29 degrees? No, right? Because this is not the whole of angle Q. The whole of angle Q is Q1 plus 29 degrees. So we've actually got to figure out first what Q1 is, and then say that plus 29 degrees is going to be equal to angle D. So if we go to the next slide, we will see there that angle Q1 is the same as angle B, basically. So that is because we've got this chord here, RT. So we're going to do angles in the same segment again. Again, you may be feeling kind of nauseous doing angles in the same segment, but it actually really helps. And I think what is good to remember is that when you look at this, you've got a chord here, you've got a chord here, you've got a chord here, you've got a chord here. There's so many ways you could do angles in the same segment. It may look complicated, but it could be your best friend in an exam or test situation. So really get comfortable with subtending angles from a chord, I would say. So here we've got chord RT, and we see that the angle that it subtends in blue, if you follow the blue dotted lines, is 76 degrees, right, which is B. And then it also subtends another angle, which is Q1, right, following the red lines, right? It subtends this angle here also. And then that's also going to be 76 degrees, right? And the reason for that is angles in the same segment. And then, of course, we've got Q1 and we've got this 29 degrees here. So we know that angle D is going to be 29 degrees plus Q1. And that's going to be 29 degrees plus 76 degrees. And so you get that D is 105 degrees. Yes, thank you, Aisha. That's correct. And yes, I'm looking at the chat. That's good. Very good. So we've got here that D is not just 29 degrees. D would be 29 degrees plus 76 degrees, right? Because it's this whole angle here, right? The whole of angle Q. It belongs to there. Or you could say it's angle PQR, right? It's the big angle here. So 29 degrees and 76 degrees gives 105 degrees. All right, so that was our first example. I hope that made sense to everybody. You can obviously put these questions in the chat. I do see a raised hand. Maybe you could type that in. Okay. And let us know what the question is. Thank you. All right. So if we can move on to the next example, I think we've got time for another one. So let's go on to example 2. Okay. Let me just erase this part. Yeah. All right. So example 2 says, in the figure, RQ and RBT are tangents to the circle with center O. Okay, so the good thing is that it labeled the center O at the points Q and B, right? So we've got tangent to the circle. It touches the circle here at Q and touches the circle here at B. So we've got those tangents. Then radius BO, right? Radius BO. This is a radius because where O is the center and we're taking a line from O to touch the circle at B. So OB is a radius. Radius BO is produced, means that it's kind of extended and cuts the circle at A and meets PQ produced at P. So it's kind of this long segment PB that it's talking about. So that's the information that we have. Now let's see what we have to find. So again, we know that this is the center of the circle. So we know that OQ, right, is going to be a radius and OB is also going to be a radius. We've got our tangents, RQ and RBT, and we also have the radius. And then, yeah, well, that's basically what we can say. We've got many different chords. It's hard to label all the chords, right? Yeah, so let's go on. In fact, OA would also be a chord. That is true. I saw that highlighted. So the first question would be, prove RBOQ is a cyclic quadrilateral. So immediately we need to think, okay, cyclic quadrilaterals, what do we know? We've got exterior angles, that the exterior angle is equal to the interior opposite angle. What else do we know? We know that the opposite angles are going to be supplementary. So it's almost kind of like you're working backwards to see which one is going to fit. Okay, so what we notice, first of all, is that we've got the radius OQ and OB there, and we've got our tangents PR and RT. So when the radius and tangents are going to meet, if you remember our diagram earlier, they're going to meet at a right angle. A radius and a tangent are going to meet at a right angle, which means that the angle RQO is going to be a right angle, as you can see in blue, in that blue box there. And it's going to be the same for OB. We know OB is also a radius and RT is also a tangent. And so they're also going to meet at a right angle, right? And so we know that angle OBR is going to be a right angle triangle. Now, we can see that we have to prove that RBOQ is a cyclic quadrilateral. Like I mentioned earlier, RBOQ is a quadrilateral. It's a four-pointed shape. How do we make it cyclic? Well, this opposite angles have to be supplementary. And are they supplementary? we've got two right angles. Does that give us a supplementary angle? It does, right? We've got 90 degrees here plus 90 degrees here. Supplementary means that they are equal to 180 degrees, right? That is, so we've got that they're supplementary. And that's why we can then say that RBOQ is a cyclic quad. So actually we've used a converse theorem. I don't remember the exact number of the theorem, but we used the converse version of it. We found that the opposite angles of the quad were supplementary, and so we can find that it is a cyclic quadrilateral. Okay. The second question there is, prove that, and I hope everyone is following so far. Let us know again if you need clarity on things. Prove that angle Q3 is half of angle O3. Okay. So again, we look at our diagram and label these points. So we've got angle Q3 over here, right? It's kind of like the pink one there. And we've got angle Q3, which is over here. So that's in purple. So we've got O3 here and Q3. And we want to prove that Q3, the purple one, is half of angle O3. So how are we going to do something like this? Well, first of all, we know that O is the center of the circle, right? So we've got these radii here. And what we know is that our radii are going to have equal angles, kind of like if you have an equiangular triangle, you've got an isosceles triangle here, right? You've got OQ is the same as OB. So Q3 and this angle B2 are going to be the same. So we can label them the same. That's why I put this 2 there. Yes, good. I love the conversation in the chat there. Let's see if you guys are right. So we can first label that because OQ and OB are the same. Then if you look at the second line of proof, you've got that O3, angle O3 here, right, is equal to angle Q3, which is here, and angle B2. Why? Well, because it's the exterior angle of a triangle. So again, this is maybe more towards triangle geometry, right? You've got OB, OQ, OB, and QB making the triangle. The exterior angle would be this O3 here, and it's going to be equal to the opposite angles. And so that, of course, is going to give you that O3 is going to be 2 times angle Q3, or you can even write it as 2 times angle B2, because we know that Q3 and B2 are going to be the same. So if you then manipulate this, you would get that angle O3 is 2 times angle Q3. Can you see angle O3 here is 2 times angle Q3, right? And then if you manipulate this to make it look like how you want in the question, you kind of just divide by half, make Q3 the subject of the formula, and you have your conclusion. All right. Again, I hope everyone's with me. Yes, that is opposite angles of a triangle equals sum of opposite angles equals sum of opposite interior. True. You can use that. In fact, there's a lot of ways you can get to the answer. I think that's what I like the most about geometry, is that there are many ways you can do it. I think maybe I picked the easiest one. All right. Question 3. If angle Q1 is equal to X, so we've got angle Q1, which is over here in purple. If that is equal to X, a chat. You can use the second theorem, a second theorem according to the slides. Perhaps I need to just double check what that is. I will. So if let's do number 3 quickly, and then I will check back to see if we can indeed use theorem 2. If you have Q1 is equal to X here, it says determine with reasons, and this is a good way, I guess, to end off our example segment. Determine with reasons 4 other angles in the figure which are equal to X. So perhaps you've already worked ahead of me. You're checking out a few things. Let's see whether we get the same answers. Okay. So we've got angle B2 first is equal to Q1. Why? Well, first, you can label Q1 on your diagram. We know that QA is going to be a chord, right? We've got circle center O, we've got QA being a chord. And if we see this, we see that the angle between the tangent and the chord, the tangent being PQ, it's not so easy to see that PQ is a tangent, maybe because it's so short, but it is because it only touches the circle once at point Q. So PQ is our tangent and AQ is our chord. And of course, we've got that the angle between the tangent and chord, which is Q1, which is X, is equal to the angle in the alternate segment, which is going to be B2, right? The angle that AQ subtends is going to be angle B2. And so we get that B2 is equal to X. Right. Now, can you see any other way? So we've got that this is X and we've got that this is X. Any other angles? Let's see. Well, again, we knew from earlier, right, that we have a kind of isosceles triangle in the middle here. And we know we've just labeled here that angle B2 is X, right? So if this angle is X, then Q3 is also going to be X, right? Because we've got an isosceles triangle here. We've got OQ and OB are the same. So if this is X, then this must be X also. All right, so we've shot down two, basically. We've got two other angles. We've got two more to find out. All right, so let's see the next one. We can also do angles in the same segment. Again, I suppose because I put the answer on the slide, it might be difficult to see these, but we should be able to label kind of different chords, right? Remember I said chords are your friend. So OB is the chord. Well, it's actually a radius, but I mean, you can think of it like that. You've got OQ is a chord, rather. You've got OA and OB would be radius. You got AQ is a chord, many other ones there. So we can keep in mind that, but the chord that we're going to be using this time is going to be OB. So what you can do is you can say that OB is subtends angle Q3, right? And it also subtends angle R2. Can you see? Pink chord, you follow the red lines, you get Q3, and if you follow the orange lines, you will get R2. So it makes that lovely zigzag pattern that we like to see. And we also know that from our previous question, remember, this is also an important point, that if you've proven something, then you can take it to be true. Right? So say, for example, in the previous question, we were talking about proving RBOQ is a cyclic quad. We take that to be true because the question that follows afterwards, yes, exactly. Yes. So that is a good point. I'm sorry, I should have probably made that a bit more clear. Thank you, Katleho. So we use the information from the previous question. That is, of course, because we're working in the same example. Of course, if you have different diagrams, obviously you'd be moving to a new question, but this is exactly the same diagram. We've already proved that RBOQ is a cyclic quad. And so that's the information that we're using going forward. In the exam, if you are stuck, let's say you could not prove that RBOQ is a cyclic quad for whatever reason, then you can still use that information in the subsequent questions. That's generally how the exam is set up. Okay, so that's what we can use here. We can say RBOQ is a cyclic quad, and we can then use angles in the same segment. Okay, so yes, good question. Good question. Thank you for that in the chat. If you have any other questions, please write them down. Yes, okay, thank you, Akira, for also mentioning that theorem. And let's see, we've got one more to go. We've got, in this case, we can use angles in the same segment again. This time we use OQ here, right? So then we look at the angle it subtends. It's going to be R1. Right, but it also subtends B2, and we already know that B2 is X, and so we get that R1 is also equal to X. So in summary, we've get that we've got B2 is going to be X, we've got Q3 is going to be X, we've got R2 is going to be X, and we've also got that R1 is going to be X. Again, you know, you may have done it in a slightly different way, maybe in your head, but perhaps, if you can kind of still reach the same conclusion, we're basically golden. And I think that's basically almost wrapping up my time. Unfortunately, I can't start another example, but if I go all the way to the end, just to quickly do a 1-minute thing, I think that these are some tips on answering questions. It's basically not to assume anything baselessly. So if they don't tell you that O is the center of the circle, you can't assume that it is. You shouldn't prove rather given information. Okay, so if they give you something, please use it. And also if they give you something in a question, you're answering a question after it, use the previous information. Then always write down a reason. I think, we get so happy when we are able to label the answers that we may forget to write down the reason, but the reason is really important. And then you will likely need to use all of the given information, in a question. So make sure if you haven't used a particular piece of information, it's there for a reason, right? So we need to make sure we're using all our information in our question. So maybe if you haven't used some of the information, you may be like, oh, okay, maybe I didn't take note of something that could help me answer a question I'm stuck on. And then remember that if you're asked to prove something, it is true. So don't find a way to prove the opposite of it or to find a converse. If they say prove RBOQ is a cyclic quadrilateral, it means it is. Okay, so that's something. And then the last point is, if you cannot prove something, then use the result to answer subsequent questions, which is something I said earlier. And of course, mark the information on the diagram. Very, very important, so that we keep a track of what's going on. So those were all the examples. I hope that you guys have followed, and I wish you all the best in trials, your examinations, all of the things. And this is our last session in term 3. Cerene, are you available at the moment?
But I don't think my connection is stable.
Okay, I'll just wrap up then. I want to say thank you to everybody for attending today. I can't put my camera on because we're in load shedding problems. But thank you for attending. And yes, we will have another session like this. Dr. Cerene, of course, is organizing everything. And you can follow the NITheCS UKZN pages to find updates on the term 4 revision sessions. I believe there's going to be 2. Thank you so much to everybody. And I hope you have a lovely weekend. Thank you so much. And all the best.